it goes to my hand. So there's a velocity in this component, but gravity has accelerated that pen downward. So there's actually two components. There's a horizontal component, right? The X, if we were to graph it, and there's the vertical component of acceleration downwards, okay? And it's a trajectory, right? If you throw a football or a basketball or a baseball or a rock or shoot a bullet or do anything, it's a trajectory, right? Football leaves your hand and it goes, right? And then the other guy catches it or it hits the ground. So an object thrown horizontally is accelerated downwards under the influence of gravity, right? The gravity is only pulling on the thing downward. So it's sort of two separate motions. There's a motion this way, and then gravity is pulling it this way. And it's the same gravity. Whether I release this pen, so if I release this pen, it's going to take that much time to hit my hand. But if I throw it, right, the force of gravity is the same. So it hits my hand at the same time. So the object's horizontal velocity is unchanged if we can neglect air resistance. Projectile motion involves the trajectories and velocities of objects that have been launched, shot, or thrown. Okay. Yeah, so I guess this is like Wile E. Coyote, right? In the cartoons, he jumps and he's there for just a second, then he falls. No, right? In real life, if this cartoon creature was to jump off the cliff, it goes down right away, right? So. Yeah, now what does trajectory look like? So here, if we had this marble, and I pushed it off a table, when it leaves the edge of the table, it's going to have a velocity. Well, the velocity stays the same in the X direction, right, on the graph, right? The distances this way on the X are the same, but gravity is an acceleration. So the distance as it's going down increase, but the distance on this side stays the same. Now the net velocity is a combination of the two, right? But that's where vectors come in. We're going to show that in just a bit. Yeah. The vertical velocity increases downward just like a falling ball. So the downward direction is just if I had just released this ball and it was just falling. Okay? And the vertical velocity, okay, so just keep in mind, right? It's going to be a velocity in the horizontal and it's an acceleration in the vertical. Now but the net speed, right? The ball it's a combination of both of the velocities. So it has the horizontal velocity, and then right at the moment when you're measuring it has a vertical velocity. You would do all your formulas to figure that out. The velocity total of the ball, you add those two vectors, and it is represented by this vector, right? Make sure you read the appendix on vectors. That was a homework problem, or a homework assignment. The total velocity at any point is found by adding the vertical component of the velocity at that point to the horizontal component at that point. The horizontal velocity remains constant throughout because there was no acceleration in that direction. So this arrow here for the horizontal is going to stay the same throughout the motion, but the arrow for the vertical is going to keep getting bigger as the ball falls and goes faster, right? So it's like two separate problems in a way. You would do this problem, there's the horizontal and there's the vertical. Yeah, so here they're just showing trajectories, right? If there was a ball and the initial velocity was to change. This is an interesting problem now. Okay, which of these three balls would hit the floor first if all three left the table at the same time? So you have three balls and you push them at the same time, but it was three different people, say, pushed them, and this person just gave it a smaller velocity, this person gave it a medium velocity, this person gave it a greater velocity. Which ball is going to hit the ground at the same time, right? Well, we kind of went over this. So it's given, right, V1, V2, V3, or are they all going to hit at the same time? Well, the answer is they will all fall the same distance in the same time. They're all going to hit the ground at the same time because the force of gravity is the same for all three balls. The vertical component, due to the acceleration of gravity, is the same. Gravity doesn't care gravity doesn't care if the ball's going this way. It pulls everything down to the ground at the same rate. So that's good to know. It doesn't matter. They're all going to hit the ground at the same time because the vertical component is the same. The force of gravity is the same. Now this one's going to travel more. V3 had an initial velocity in a horizontal direction that was greater, so it's going to travel more. But all three, and then if you had a ball here and you dropped it just straight down, they're all going to hit the ground at the same time. Good stuff, right? Cool. Yeah. Treating the vertical motion independently of the horizontal motion and then combining them to find the trajectory. That's the secret. And we're ignoring air resistance, right, in all of these. Yeah, so if there's a person doing, target shooting like in the Olympics, right? If he's aiming at the target and he was to shoot this gun perfectly level, well, the bullet would drop and it would hit below the target because gravity is acting on that bullet the whole time. So what really happens, and you don't see it because it's slight, but if you're shooting a gun, here you're showing a football, but it's actually aimed up a bit. And it'll follow a trajectory to hit the target, right? So anything, right? A football player, you can see it. A football player, we all know he can't throw the football directly straight at the receiver. It's going to hit the ground. He has to throw it at an arc, right? Well, bullets go fast. You can't see them, but bullets are doing the same thing, right? It's going to be less. Okay. Yeah, trajectory depends on the initial velocity and the launch angle. Yeah, so just something that's good to know, right? If you throw something straight up, it's going to land straight down. If you throw it at a slight angle, it's going to go, up and it's going to land, right? But you also know that if you throw it too close to the ground, gravity's going to affect it, it's going to hit the ground. Well, what angle gives you the greatest distance? It's right in between 45, right? We all know that. Right, a right angle is 90 degrees, right? 45 degrees. So if these two markers are 90 degrees, 45 degrees is the midpoint. That's the point where if you throw a football or fire a cannon or do anything, right? It's with the same force, you're going to get the longest distance that way. Okay. Yeah, and then again. You're adding the vectors as well, right? Okay. If these vectors are all the same value, well, if it's a really small angle, it's going to hit the ground because gravity is going to pull on it. If it's a high angle, it's almost like throwing it straight up. It's just going to come down right not far from where you threw it. 45 degrees is going to give you the most distance. Yeah, 45 degrees. So that's just good to know, right? So when they're playing football and the quarterback is throwing it way, you know, a Hail Mary, he wants to win the game in the last seconds, he's going to try and throw it, and he wants to get the most distance, throw it at a 45-degree angle. Okay, and I think that's just some other problems. We're not going to talk about all the different sports here. Baseball. Okay, folks. That's it.